Welcome back to our networking layer module, and today we're going to go deeper into the routing, and specifically we're going to be talking about one of the routing protocols. So the protocol we're going to be talking is RIP, or Routing Information Protocol. I put up on the slides version 1 of the protocol because it's one of the basic protocols, like the first one was defined. Essentially, RIP is a distance vector protocol, and I hope you already remember what distance vector protocol is. One specific difference is, or specific definition in the RIP protocol is the maximum length that you can go is 15 hops. And effectively 16, hop number 16 means you reached infinity, and if you remember the count to infinity problem. And that's basically stopping point. A few comments about the protocol itself. So the RIP protocol works on top of UDP. It uses this specific port 520, and it has exactly one message defined. So this is the message, or the packet format that I'm showing on the slide is the one message in this protocol. And this message is acting as a hello message, so basically to advertise router's presence in the network. Plus, it's also acting as a in exchange of information about what you can reach. And as you can see, there is an IP address and some form of metric, simply saying if I'm sending this message, and as me is identified by basically the source IP address of this message, is saying that router can reach this IP address with certain metric. One thing I want to note about specifically version 1 of the protocol is the fact that it only contains IP address. I hope you remember that when we talked about the routing tables, we always have some notion of subnetwork mask, and somehow this is not part of the version 1 of the protocol. And a simple reason. So this protocol was actually designed before we switched to classless interdomain routing. And basically from the IP address, you can, before we switched, you can always infer what kind of network it is. Whether it's a class A, class B, class C, and basically understand from that what you're doing. Unfortunately, this was not backported to the RIP protocol of version 1, but it was lately added in version 2 and version 3 of the protocol. But remember this interesting fact of this protocol. For your information, I just included the Wireshark capture of RIP protocol. What you can see on a slide is kind of multiple messages from two hosts in this specific network, and they're simply advertising what they can reach. In this message, you basically can see that one of the routers is advertising 4 networks, as you can see in the bottom of the screen. And from the perspective, is simply saying it can reach 10.0.3.0 with metric of 1, it can reach 10.0.4.0 with metric of 2, and 2 other networks with metric of 1 and 2. One thing that you will notice later, after we're going to be talking a little bit more about that, but already here you can notice the timings of those messages. So you can see, if you're looking from the router 2 and router 2, those messages are being sent out around every 30 seconds. So that's one of the important timers for RIP protocol. This is exactly the same thing that I was just talking before, just a little bit expanded in a graphical form. So maybe it's easier for you to understand when you're looking at the slides later. Now getting to the example. Today I'm not going to be talking too much about the actual calculations of RIP protocol, because it's basically the same distance vector protocol that we already talked before, just very, very high level highlights of the protocol. So essentially, if we have a node A announcing some distances to and kind of sending this message to node D, this is basically node D responsibility to evaluate this information and maybe recalculate some of the kind of costs and potentially next hop. So in this specific case, it's discovered that reaching destination Z somehow is cheaper through A by some specific magic. Maybe there is additional path available to Z that's not shown on this picture. And there is updated cost instead of 7, and that was in original calculations. Now the cost is 5 because it has internal understanding that from D to A it is 1 hop. And just in case in RIP there is a kind of assumption that all costs for each individual link is 1, and you cannot really change that. And that's basically it. And potentially in the future exchanges, D can advertise it to B, B may also recalculate, and so forth and so on. That's the basics. Now getting to actual protocol actions of RIP. So the important part of the routing protocol is not just calculate the routing table, but rather detect that something bad happened and react to those changes, basically to notify others that something happened, or at the very least to recalculate their own routing table. And one of the timers, and I'll show a little bit more later, is this 180 seconds. So basically the idea is if you don't hear any update from the neighbor for more than 180 seconds, you declare it's dead. And if I already highlighted that each neighbor is sending a message every 30 seconds, so you have to lose a lot of messages in order to, to be considered as dead. And the reason we send in this every 30 seconds is because we're relying on the UDP protocol. And if you aware from the and you're already well aware from the project too that the UDP message is unreliable and they can be lost at any point of time. So basically, that's the basic idea. What can happen if you receive the update that it changes, you can actually kind of send updates immediately if you recalculate something, but usually a RIP protocol does not send out anything as in reaction of received updates, simply because the new update will be sent out within 30 seconds. So basically you can assume you receive some update, even if something changes, you locally recalculate your routing table, but you do not send out any information outside if you have some new information. Because this is like, all these changes are quite rapid. And on top of that, we're still using poison reverse in order to prevent some form of ping-pong looping. And as a small illustration, if we consider state at node D, so initially, let's say, assume that D already calculated all the state, or received the previous information, and it knows that how to reach W, it needs to go to A, and it's a cost of 2. To go to Y, it needs to go to B, Z, and so forth. So kind of in normal case, it will simply send out updates to B and except Y, because Y is reached through B, everything will be actual cost that was kind of in the D state. And for Y, it will specify 16 because that's poison reverse. You basically tell others that you cannot reach them, just simply saying 16. If, for example, we break link between A and D, what will happen at this point, like at the next update that D will be sending to B, it will simply inject this poison reverse to the B's direction. So basically, for all routes that were that the D knew how to reach through A, it will simply say, oh, now I can reach only through 16, and Z I will reach only through 16. Basically, this will be some form of kind of notion of lost route towards that destination. And again, this will happen after 180 seconds, after not receiving at least 6 updates, like 6 hello updates from A. And as soon if A at some point later actually sends out the message, then all the routes will basically reappear and will be re-advertised by D. Okay, so as I said, there is a few more timers, and actually there is one more timer, is a garbage collection timer. And the thing is, when you declare someone dead, you actually don't immediately remove that information. And the reason for that is that poison reverse. So you still want to notify others for a certain period of time that you cannot reach them. Because if you remove them from your own state, then there's nothing to kind of advertise because you don't have knowledge. But if you keep them, then you'll be able to say this 16, I cannot reach that information. So basically, this is what the garbage timer is trying to achieve. So for next 120 seconds, if you still didn't receive any update from A, you will keep this poison reverse, and after 120 seconds, you simply remove that information and kind of assume everybody got those updates. Some of the extensions of RIP protocol actually have the concept of RIP, or routing information base, and the difference is a routing information base contains all the information you obtain from the neighbors, versus FIP, or routing table, is just the shortest path. And so normally, for the advertisement purposes to neighbors, you use a FIP, but internally you still can keep some information for additional route about additional routes. And for example, if some route failed, you can immediately switch to the other one because you already have that information available. Whether it's working or not, it's a good question, but at least there is such a possibility. And garbage collection, that's the just simple illustration what I was talking before. If you declare something dead, like after not hearing for 120 seconds, then you can declare them dead inside the forwarding information table, but you keep the record. And you just keep advertising poison reverse information toward that destination. Just a few small highlights about the implementation. There's a multiple implementation of RIP protocol. So one of them, I think it's legacy implementation, is as part of this route D daemon. It's basically the application process that contains its own RIP. And whenever it's received messages, it's simply updating a routing table or forwarding table in the kernel of operating system. And I think you can run it on some BSD systems. I'm not sure it actually exists on Linux operating system. What you can do instead, that's basically much more popular variant of routing protocols, is a Quagga software suite. So this one is actually supporting multiple different routing protocols, the one that we already talked, the RIP protocol, and a few more that we'll be talking, the OSPF and BGP. And in addition to that, there's also more stuff, and people actually inventing new routing protocols and implementing, at least for the experimental purposes, as part of this Quagga suite. And a just interesting note about Quagga. It was actually called Zebra, like in original software that was developed, and then that software got stalled, and kind of new people came in, and they decided to kind of revamp the implementation. So they kind of created a fork of the software and called it Quagga. But it's basically the same software, and they actually kept the name of the module called Zebra, like as part of that implementation. Just a small highlight of newer versions of RIP protocols. We actually have 3 of them, 2 new versions. One of them kind of trying to implement some form of hybridness between distance vector and link state vector, still having the metric of 15, so it's not really a great solution. They're trying to use the multicast address instead of just broadcasting to the neighbors. And for the even more extensions of the RIP protocol, they're basically trying to add the support of RIP protocol in IPv6. So that's kind of major highlights of this RIP NG. Just a tiny highlight. People actually don't like using RIP protocol because it's a little bit too rigid because of you can only have this metric 15. There is this potential of some form of routing loops, and sometimes the reaction time is not that great. But it's really easy to set up, and you don't really have to disclose the topology, even though topology is expected to be quite small. So there's still a tiny use of RIP protocol, but it's not that popular. Okay, so now done with the RIP protocol. Just remember, RIP protocol implements distance vector algorithm. It also includes the split horizon with poison reverse to avoid some problems when a link failed. And the protocol side of RIP is basically that it uses a single header, the format that I showed you on one of the first slides. It uses UDP protocol and specifically port 520. And the single header type is used as a hello message to advertise yourself and as an advertisement of what routes you can reach. Timing, remember the timers. I think I counted 3 timers so far. And for the actions, there are basically actions of recalculating the routing information and forwarding the information as soon as you receive some new updates. There is some form of a dead list when you declare that the node has been not reachable, and you keep that dead list for a certain amount of time, and there is another timer to remove the list. Okay, I promise that this will be intensive, even the number of slides is not that big. But it is important to remember that the protocol side of the routing algorithms, you have additional kind of understanding of how to advertise yourself, how to detect others, kind of what others advertising, and detect when others are kind of leaving the network and what to do with them. Okay, so that's it for RIP, and see you next module.